The Vector Index Traversal System, referred to internally as VIT, is a component responsible for efficient navigation through multi-dimensional vector spaces stored in indexed columnar format. The system operates within a read-only context following index materialization. All traversal operations execute against pre-computed index structures. No write operations are supported during traversal phases. The underlying data model assumes vectors of fixed dimensionality populated during the index construction stage. Index structure initialization begins with dimension validation. The system verifies that all input vectors conform to declared dimensionality before any traversal operation commences. Dimension mismatch errors return code error dimension mismatch. The initialization phase establishes internal pointers to root nodes within the hierarchical tree structure. Memory allocation for traversal state occurs at this stage. All allocations are released upon completion or explicit cleanup invocation. The node traversal algorithm implements a depth-first search pattern with optional breadth-first queuing. Node structures contain dimension-aligned partition boundaries and child node references. Each node maintains a payload count indicating the number of vectors it represents. Traversal decisions occur based on distance metric evaluations against partition midpoints. The system supports L2, L1, and cosine distance metrics through pluggable distance function interfaces. Pruning mechanisms reduce computational overhead during traversal by eliminating subtrees that cannot contain relevant results. The pruning algorithm maintains a distance threshold derived from already discovered candidates. When a partition's minimum distance exceeds this threshold, traversal of that partition ceases immediately. Early termination improves performance for k-nearest neighbor queries. Pruning decisions are reversible during backtracking operations when threshold updates occur. Query parameter structures define search behavior and termination conditions. The k parameter specifies the number of nearest neighbors to retrieve. The radius parameter constrains results to vectors within a specified distance. The max depth parameter limits tree traversal to specified levels. Default values are k equals 10, radius set to maximum float value, and max depth set to tree height. All parameters are optional and may be omitted to use defaults. Result collection mechanisms maintain sorted candidate lists during traversal. Candidates are stored in a priority queue ordered by distance from the query vector. The queue implementation uses a bounded binary heap for efficient insertion and removal. When the queue exceeds capacity equal to the k parameter, the furthest candidate is discarded. This maintains memory efficiency during traversal of large indices. Cache coherence during traversal is maintained through read-only access patterns. The system does not modify index structures or node data during query execution. All state changes occur only in traversal local data structures. This design allows multiple concurrent traversals without synchronization overhead. Cache line contention is minimized through padding of frequently accessed fields. Index data remains eligible for standard OS page caching mechanisms. Distance computation caching reduces redundant calculations during traversal. The system maintains a thread local cache of recently computed distances. Cache keys are constructed from query vector coordinates and node partition centers. Cache entries expire when the query vector changes or explicit cache invalidation occurs. Cache hit rates typically range from 40 to 70% depending on vector dimensionality and dataset characteristics. Leaf node iteration mechanics differ from internal node traversal. Leaf nodes contain direct references to vector identifiers and their storage offsets. During leaf iteration, the system examines each vector individually against distance thresholds. Leaf nodes maintain insertion order metadata allowing secondary sorting by temporal sequence, if required. Pagination support allows iteration of leaf contents in configurable chunk sizes. Backtracking procedures are invoked when the current traversal path yields insufficient results. The algorithm maintains a path stack recording the sequence of nodes visited. Backtracking pops nodes from this stack and explores alternative branches. Distance thresholds are reevaluated after each backtrack operation to determine whether previously pruned subtrees should now be examined. Backtrack operations preserve all discovered candidates, ensuring result monotonicity. Error handling during traversal follows consistent fault classification. Index corruption detection returns error index corrupted when checksums fail. Memory allocation failures return error allocation failed. Invalid query vectors return error invalid query. Timeout conditions return error traversal timeout. All error codes are documented integers beginning with the error prefix. Partial results. may be returned for timeout conditions if requested through the allow partial results parameter. Memory consumption during traversal scales with tree height and results set size. The traversal state structure requires approximately 512 bytes plus allocation for the result priority queue. The priority queue requires 8 bytes per entry multiplied by the K parameter value. Large K values should be avoided when memory constraints exist. Memory usage is predictable and does not exhibit pathological growth patterns. Concurrency considerations permit multiple independent traversals on the same index structure. No locks are acquired during read-only traversal operations. The index structure itself remains immutable throughout the traversal lifetime. Thread local state isolation prevents interference between concurrent queries. Atomic operations ensure consistent visibility of query results across thread boundaries. No memory barriers are required beyond standard query semantics for result publication. Performance profiling hooks remain embedded within the traversal system for diagnostic purposes. Elapsed time measurements track duration of each phase separately. Node visit counts indicate traversal depth and breadth metrics. Cache operation statistics reveal hit rates and eviction frequencies. These hooks incur negligible overhead when disabled through compile time configuration. Production deployments typically disable all profiling instrumentation. Result formatting mechanisms encode discovered neighbors in structured output formats. Each result entry contains the vector identifier, computed distance value, and optional metadata. Result ordering defaults to ascending distance. Descending order is available through query parameters. Result encoding supports JSON, binary, and protocol buffer formats. Result completeness is guaranteed within numerical precision limits of the distance metric implementation. Resource cleanup. Following traversal completion releases all allocated state structures. The cleanup operation invokes destructors on the result queue and traversal context. Path stacks are deallocated. Cache structures are cleared. Thread local storage is returned to available pools. Cleanup is idempotent and safe to invoke multiple times on the same traversal instance. Failed cleanup does not prevent subsequent traversals on alternative query instances.